We now begin to jump ahead a couple of centuries from ancient Greece, specifically at the end of the 1st century AD and into the 2nd century, we get to an important Roman astronomer named Ptolemy. This is roughly the 1st century AD, the end of it. As we'll see, Ptolemy is important for a number of reasons in this brief history of the early history of astronomy. With respect to Ptolemy, however, the first thing that he's important for our purposes is he made the following measurement. He devises an exact means of finding the distance from the Earth to the Moon, and he does so by using what is called parallax. Determine the exact distance from the Earth to the Moon. Okay, now you can demonstrate parallax for yourselves. Do the following demonstration as you listen to me lecture. Take first of all your index finger and hold it out at arm's length as I'm doing here. And then close your left eye and then look at your index finger with your right eye. And notice the position of your index finger relative to the more distant background. And then close your right eye and then open your left eye and look at your index finger again. You're going to see that your index finger appears to have shifted with respect to the more distant background. If you blink your eyes back and forth like so, as I'm doing here, you'll see the position of your finger shift against the more distant background. You're seeing an angular displacement of an object in the foreground with respect to the background from two slightly different locations, your right eye and your left eye. That angular displacement, like so, is what is referred to as the parallax angle. So using this method of parallax, Ptolemy devises an exact means of determining the distance from the Earth to the Moon. Here are the details of his calculation. Okay, so first of all, we have the Earth, like so. And then let me draw this line. And let's say that right here is the center of the Moon. Right here is one location on the surface of the Earth. We then look at the Moon like so, and we see the Moon have a position with respect to the more distant background stars. Like so. Okay, and now at the exact same time, you have a second observer on the Earth at a different location looking at the Moon at the exact same time. I'll draw that like this. Okay, right here is the second location. Let me go ahead and draw this line. Like so. Such that if you were standing here and looking at the Moon in this direction, here is the center of the Moon, so the Moon is like this. On the diagram, you'll notice that you see the Moon against a slightly different background. Okay, let me correct this and make it more straight of a line. Like so, that's a little bit better. But you'll see the Moon here against a slightly different background. So then therefore there is a shift in terms of the angle that you see the Moon in the sky. That is this angle here. That's the same as this right here, this angular displacement. It'll be a little bit more careful about the terminology. That's then what you see, for example, when you blink your eye back and forth and look at the position of your index finger from a slightly different point of view. That's the parallax angle. The parallax angle is usually referred to as beta in this description. And it's measured. Okay, and then on this diagram, something else is measured. Right here at the second observer's location, this dotted line right here is towards the zenith. It's straight up at that location. And then we're looking at the Moon like so on an angle. Right here on the diagram, this angle here is usually referred to as alpha, and that's also measured. And then we also know a distance on this diagram. The distance on this diagram that we know is right here. This is referred to as A in this description, and this is the radius of the Earth. We've known what the radius of the Earth is from a couple of centuries prior with Eratosthenes' calculation. So A is the radius of the Earth. And this is known. Okay, so we've got these two angles here on this diagram that are measured. This distance A is known, and then right here is a triangle. Basically, now what we do is we run through a little bit of trigonometry to figure out all the sides of the triangle, nothing more than that. This is most easily done, however, if you take this big skinny triangle here and divide it up into two right triangles. Like so. So here's a right angle, and let me go ahead now and start to label a couple of things. First of all, we're going to need some angles. This angle here, I'm going to call gamma. This angle here, I'm going to call delta. This side here, I'm going to call B. This side here, I'm going to call C. And lastly, this dotted line right here, I'm going to call D. What we're going to determine is B plus C. B plus C is the distance from the center of the Earth to the center of the moon. Here are the steps. The first step is to find the angle gamma. Notice that it's the supplement of alpha, which is measured. So gamma is 180 minus alpha. Okay, and then next we determine delta. Delta plus gamma plus beta is 180 degrees. The sum of the angles in a triangle equals 180. So then therefore delta is equal to 180 minus gamma minus beta. So now we know what delta is. And then next we take a look at this little right triangle here, and we use, first of all, a little bit of cosine to find side B. So to do so, cosine of delta is equal to the adjacent side B divided by the hypotenuse A, which remember is the radius of the Earth. So cross multiply a little bit, and B is equal to A cosine of delta. Okay, then next we find the distance D. This can be done a couple of different ways, but probably the easiest way to find the distance D is to just do a little bit of Pythagorean theorem. Notice that B squared plus D squared is equal to A squared. Remember, we know what B is. We just determined that a moment ago, and A is the radius of the Earth. So now solve for D. So subtract the B squared to the other side and take the square root. So distance D is the square root of A squared minus B squared. And then the last step of the trigonometry is to find C. We'll do so by using a little bit of tangent with beta. Notice that tangent of beta is equal to the opposite side D divided by the adjacent side C. Remember, we know what D is. We just found that a moment ago, and beta was measured. Now just cross multiply and solve for C. So C is D over tangent beta. And then the distance from the center of the Earth to the center of the moon is B plus C. So what was Ptolemy's result? Ptolemy's result was very accurate. And this is an extremely important number for later on when we eventually get to gravitation. But for now, the distance from the center of the Earth to the center of the moon is 60 Earth radii. This was Ptolemy's result. Ptolemy's result is very accurate. That's the distance from the Earth to the moon. So one of the reasons why Ptolemy is important is because he made this calculation. He's also important for some of the topics that will follow a little bit later on. That concludes this lecture on Ptolemy.